Yeah, I got an interesting sort of email from Martin earlier today when he said, my flight was canceled. Can you please come give this talk? And it's in an hour and 15 minutes, so you've got a little bit of time to prepare. I looked at it and said, Martin, did you know that Halifax is not on Eastern time? So it turns out we had 15 minutes to put this together. So I can ask you some level of forgiveness here. I'm not Martin. I do have his slides. I don't have his jokes. It's funnier in the original German. But we'll see how this goes. So folks like deep learning? Folks hate deep learning? Folks indifferent about deep learning, waiting to be convinced skeptically from the back row and chuckling silently to yourselves? Okay. So I think deep learning is pretty interesting. Personally, I'm not one of those dyed-in-the-wool deep learning converts who lived through 3 different AI winters only to emerge victorious. But I think it's an extremely useful set of tools that has allowed us to move into a really interesting world of perceptual data and the kind of data that doesn't look like something you would stick in a spreadsheet. So I imagine Martin is a wonderful fan of cherry blossoms here. And the sort of learning that we're able to do on images now is qualitatively different as a field, not just because of TensorFlow, but as a field, than we were doing, say, 5 or 10 years ago when search engines were doing a great job of mining links and doing some statistical analysis on word frequencies and things like that to figure out if something might be a cherry blossom image because of the words around the image. Now we're actually looking at the images and we're doing, pretty deep level understanding about what's going on in the image. And this is true not just for cherry blossoms, but for any number of slightly opaque icons at Google. So we've got deep learning is now, in many ways, the go-to solution for highly complex systems, especially where we have extremely large amounts of training data. Where extremely large, you can arm wrestle about who's got the largest data or things like that. But when we're in the high millions, billions of examples, deep learning seems to work pretty well most of the time. And so we've seen this to be true for a bunch of production systems at Google, whether it's in Google Play or YouTube, where video analysis is being done, various sorts of online advertising applications, and everything else in the gamut. It's not just internally to Google. So this is a Japanese family that does cucumber farming. And you can see that this gentleman in the back is the son of this couple. And this son decided that it would be useful to be able to sort cucumbers using computer vision and put together a cucumber sorter using open source TensorFlow with not a whole lot of effort and not as some highly paid data scientist, but as someone who needed to solve a problem in their daily agricultural work. So I think that this sort of democratization of machine learning is also kind of new in the way that the renewed success of deep learning is kind of new. And to me, very interesting. I think that this is opening up a world of possibilities. So Martin's making this strong claim. I'm not necessarily going to stand him up. I might throw him under the bus a little bit. Anything we can do, machine learning can do better. Yeah, maybe. I certainly think that anything we can write down with a formal objective function and observe with a large amount of training data that we think is coming from a source that's reasonably similar to the source that we'll be applying it with at inference time, yeah, that's a pretty large class of tasks. And as a task of class, those tasks are probably things that we should be using machine learning for. And in particular, deep learning seems to be, a reasonable first approach for a lot of these large-scale tasks. So anybody who's sort of been around the world of machine learning knows that in reality, machine learning systems can indeed become reasonably complicated reasonably quickly. And here we're going to talk just about the models, also about the systems that train them, I personally have a small cottage industry of complaining about technical debt in machine learning, and so I can wax about this forever, but this is Martin's talk, not mine. So if we're thinking about neural networks, okay, we've got data coming in, data going out. Folks are familiar with neural networks? Okay, if we're looking at these little circles and I describe them as neurons, that's not going to disturb anybody here, I would imagine, and the connections between them are by now, widely familiar to us. But they don't really look like this nice little row of 3 layers and 4 neurons per layer, unless we're doing toys or impressing our children. Here's a model from the dark ages of 2015. This is an Inception model that at the time was state-of-the-art on ImageNet, image recognition stuff. And I think the point of this slide is to impress you with the incredible complexity of the Inception network. And I would argue that if anything, this kind of undersells the complexity of the network, because each of these little blue boxes here is, in fact, a reasonably complicated set of layers in itself. So these things are reasonably complicated. State-of-the-art right now seems to rely on smart humans or overworked graduate students to come up with the right network. And so this is an area where I think we have room for active development. My colleague Ben is smirking over there in the corner because he's working on solving this problem automatically for all of us, and Ben, it'd be great if you hurried. Okay, so just the training network is one interesting thing, one source of complexity. But we can also think about the system-level architectures that happen. So if we're making a prediction, we've got the parameters that go into that model. Hopefully those are stored somewhere where we can access them easily. And if we're in some sort of real-world system, we are very likely not just training this model once and deploying it and saying good luck forever, but we're probably collecting some additional data over time, making updates to that. If we're working off of a large set of training data, then we're probably not doing, say, gradient descent over that full batch, because that's what silly people did in 2001. We now do MiniBatch gradient descent as sort of a go-to method. And so we need to find some way of chopping these little input batches up into smaller pieces. When we've got lots of pieces, then now we can train these guys in parallel. And so we need some sort of parameter server kind of architecture. TensorFlow supports parameter servers. There are plenty of other packages that do as well. So we can think of now parallelizing. We've got this guy here as a little worker task that's going along and making predictions as it trains so that we can get our gradients for updates. If we're parallelizing it, we need to stick this thing in a lot of different areas, and basically having it, each of these model shards are now looking at batches of data, training along and sending their updates to a shared parameter server that's probably also parallelized. And yes, okay, we are indeed parallelizing. We're parallelizing the reading of inputs. It's important to parallelize input reading because reading from disk remains really expensive. And we're seeing large accelerations in sort of, processing speed and things like that, but reading from disk, that's still kind of slow. And at least to my knowledge, we're not seeing the kind of accelerating curves on disk reads that we're seeing in other areas. And maybe you're not reading from disk. Maybe you're reading over network or things, other sort of horrifically expensive things. So parallelizing the input stream is quite useful. Also, these models can get pretty large. If we're keeping a couple billion parameters around and maybe complicated networks or whatever else, it can be very useful to have a number of machines storing those parameters. And machines are flaky, they're finicky. It might be really useful to have more than one copy of a given parameter for basically fault tolerance. So parallelization can be quite useful. But I'll also argue that for any sort of real-world machine learning platform that we're actually going to use to solve real problems in real businesses or real environments, it's important that we have some concept of portability. I would argue that it is absolutely no fun for me to write code that works well on my desktop and then have to completely rewrite that same code and model training for it to run in a distributed setting, and then for me to completely rewrite that same code for it to work well when training on GPUs or TPUs, or if I'm going to then go and deploy it on phones, because apparently now this is where the world lives. I would very much like that to be a write one sort of experience. And not just because I'm lazy, although I am, but because it's quite frequent for small differences in pieces of machine learning code to show up as much larger differences than you would like at training or inference time. And I see some nods on that one where, even things like floating point roundoffs can actually end up accumulating in very different ways on different architectures. And you'd like to solve that problem once, as opposed to solving it every time you create a model and try and port it around. So this idea of portability is sort of fundamental to the architecture of TensorFlow. We can argue about whether TensorFlow has gotten that completely right yet, but it's at least the goal. Okay, and yes, of course, because we're all, technology people, we've all got Raspberry Pis at home that we're using to teach our dogs how to do machine learning. And so, yes, we work on Raspberry Pi as well. So we've got this environment where we need to be able to handle heterogeneous systems, where we need to be able to do distributed training and potentially distributed inference, and where we need to be able to handle large amounts of modeling complexity. So yay, hooray, TensorFlow. We do believe that TensorFlow is a reasonable solution to this set of, I don't want to call them constraints, but I would certainly call them wishes. We have strong wishes to be able to handle each of these varying requirements. Okay, so how do we do this? Well, obviously, if we're going to support a wide variety of devices, at some level we have to write device-specific code. And that's the piece that TensorFlow tries hard to abstract from the developers. So down here we've got little kernels that are implemented to work on different devices. We then have the TensorFlow distributed execution engine that knows how to talk to these kernels, and then a front end that knows how to talk to TensorFlow. So there's a little bit of indirection, and if you've worked with TensorFlow, you may find that some things like figuring out when exactly your op is being called in a graph can lead to a little bit of learning opportunities, but it's sort of necessary to get this kind of useful stack going. So let's think about how TensorFlow is used in practice. I sometimes talk about there being two paradigms for machine learning systems, one in which you train in a big batch and then do large inference, and another where you're doing sort of continual training, so online training or something like that. I've now decided that online training is basically a lie, because every system I've ever seen really does sort of a staggered continual version of the batch setting, where, okay, maybe we're doing it at 15-minute intervals where new data comes in, we retrain, we get a new version of the model, and we ship it out to serving, but we're not really doing it every microsecond, right? The data may be coming in on a continual basis, and we're kind of storing it in pools, but in terms of like actually shipping a new version of the model out, that seems to be happening in most of the large systems that I've seen at, minutes to hourly kinds of cadences. So I would argue that thinking about this sort of, train it, then ship it off to inference paradigm is going to cover a large amount of use cases. You could ask interesting questions about, okay, well, what about your mobile phone or things like that? They're trying to learn in situ, and we could argue about that later. So if you're only thinking about inference, then essentially what you can do is train up your model, stick it in a binary, put it in TensorFlow Serving, which accepts RPCs. And TensorFlow Serving is a nice package that's open source as well. And then you can just go ahead and write your input processing code and the code that figures out what to do with the predictions in the language of your choice, and just ship off RPCs to TensorFlow Serving and basically be language agnostic. I think that's a reasonable model. it might be that TensorFlow is training that model in the background. But if we're using gRPCs, then we're able to be abstracted out reasonably. Okay, so let's then think a little bit more about training, because I just gave a really hand-wavy explanation that, okay, serving we don't have to think too much about. In the real world, of course, we need to think a lot about serving because servers go down or latency becomes an issue or things like that. But at least from an architecture standpoint, I'd argue that if we're able to rely on RPCs, we're reasonable there. Okay, so from a training standpoint, we've got data coming in. As I said before, we want to make sure that that data is being able to be processed in some kind of parallelizable situation. Gets sent off to trainers, those little model shards that ship off their parameter updates to a parameter server. So, and I just told you all about why I think the word continuous training is a lie, and this is what happens when you get the slides 10 minutes before. Okay. We do happen to have a paper, as Google here, about a continuous training system. If you look under the hood, it's really a batch system that operates really quickly. But there is a presentation on this later at KDD. The title of it is something like TFX. And it's I think, a reasonable explication of the additional pieces around any production level system that you'd want to make sure that you had built and that we describe in some detail there. I think that of the pieces of that pipeline that are probably the most surprising to someone who's only worked in academic machine learning are needs around validation of a model before it's being shipped out, where model validation we often think of in terms of, okay, let's use a validation set to make sure that our accuracy is still good. In a world in which you're using an open source package that may update over time, validating that your code is still, say, op for op compatible with the version of the code that's doing the training and the version of the code that's doing the serving is another sort of validation that's quite important in the real world. And this other paper talks a bit about that as well. Okay. Let's see. So, yes, we do believe that deep learning is pretty good. Hooray. I'm just going to go ahead. I'm going to completely disregard this third bullet point here where Martin is claiming that no or little domain expertise is needed. Here at KDD, I think that this community has learned quite well that having access to domain experts is almost always to the benefit of the project. Anybody ever found that to be true? Yay, domain experts? Okay. Anybody like, oh, let's forget all domain experts, time to fire them all? No? Okay. All right. So I do believe that domain experts are incredibly useful for most areas. That doesn't mean we need to hire 10,000 statisticians if we're building a translation model. But it does mean that we don't want to be guilty of, say, ML chauvinism or something like that, where we think that ML is going to solve all the problems for us and we don't have to look at the data. End of rant. Okay. So if we're building up these models, we probably have a domain expert who's helping us out here. We probably have a couple of folks who are good at model building. But as a manager, I don't necessarily want people writing every single ReLU layer they ever use from scratch. Even if they're really good at it, it's not a great use of their time and introduces bugs and errors. So TensorFlow now provides a set of layers that has been standardized. And this is in TF layers. And these include things that you can think of as Lego blocks. But have you guys seen Legos these days? I have an 8-year-old daughter and an 11-year-old nephew. My 11-year-old nephew just built this 10,000-piece model destroyer that he designed using CAD and then had all the blocks printed out. And so I think the Lego metaphor has just gotten substantially more powerful than the Lego metaphor was when I was a kid. But anyway, so these are very powerful Legos. So some of these Legos, we have layers that allow you to do various kinds of embeddings, which can be useful for inputting text or other sorts of sparse data. We've got layers that allow you to talk about different kinds of deep network layers. So things like a ReLU layer is a layer that's available. I think there's even a ReLU 6 layer, if I remember right, which is a ReLU layer where you cap off the maximum value at 6 because log never goes larger than 6, I guess. We have various convolutional layers that can be useful for image processing, also useful for audio or video data. We've got recurrent layers. So I don't know if we've gotten to the end of the LSTM fad. You guys remember that when SVMs were a fad? And then that was what, like, tail end of that was probably 2006, 2007. I would argue that the LSTM fad may be ebbing as of July with the publication of a paper on Archive saying that attention is all you need and LSTMs are basically overkill. However, if you still like LSTMs, even though it's now August and not July, we do have some excellent LSTM layers. And these things are pretty interesting, even if you think they might be overkill for certain situations or computationally too expensive in other areas. They do seem to still be doing awfully well at a bunch of tasks, including translation. And the idea here is that this is now a model that keeps some amount of state along with it. So that state can be used to think of, say, what's happened previously in a given sequence of words or things like that. So if we're thinking about, you know, a toy problem in question answering, you know, you might say, okay, if I'm just looking at these images, you know, what's the man doing? Well, he's packing. What color is his shirt? Blue. And if I've designed the system, I'm really thrilled because it just did a good job of question answering on 2 natural language questions. The way that this thing is built is it's got an LSTM that's based on the frame and video sequence of the data, and an LSTM that's based on the sequences of words. And these guys mix together into a larger network. What's kind of funny, though, is that if you didn't take sequence information into account, you might not be able to tell if he's packing or unpacking the car, looking at any one of these frames, right? So this is sort of the cartoon justification for why sequences are important and why we may need to think about LSTMs. Okay, so then let's look at things above layers. I've been talking for a lot. I haven't asked this question. Who's actually written TensorFlow code here? Okay, all right, great. So my colleague Ben, again, shamefully raises his hand up to about there. All right, so if you haven't used TensorFlow before, the good news is it's possible to build really complicated models quite quickly. The bad news is that if you're just using raw TensorFlow, the other pieces can be more sort of boilerplatey than you'd like. In particular, things around pulling data in, processing it, writing checkpoints out to disk as you're training, various things of that sort. So we've put together this package up a lot of that boilerplate code and make it so that we don't have to keep writing the same training loop over and over and things like that. So there's a poster about the estimator library. Excuse me. There's a poster this evening about the estimator library. Martin Wick is also going to be presenting that, so I may see you there. But the paper is titled Train and Distribute, and it's a relatively in-depth look at this library, which I think is quite useful. Okay, so what that library does is help you know, with the various batching and parallelization and things like that. Okay, another thing that's nice about TensorFlow is we've got this reasonably robust set of tooling around monitoring training. This is called Tensor Board, and Tensor Board comes with open source TensorFlow, and it gives you nice little graphs on your training loss over time. So you can tell that it's we're not non-convex optimization led anymore by these funny bumps over time. But TensorBoard offers a number of useful things, including a pretty cool Embedding Explorer that allows you to sort of zoom around in your embedding space and try and get some understanding of what's going on in there. It allows you to do some amount of checking for nans or other numerical instabilities. It's a reasonably useful tool. And for my money, if I'm choosing a machine learning package, trying to be as unbiased as possible, I would argue that in many cases, it's the supporting tooling that really makes the difference in your experience as a day-to-day developer. Okay, so TensorFlow removes complexity, except when it adds it. So indeed, TensorFlow does remove complexity from the porting of models from device to device. It does hide a lot of complexity around distributed computation. And through the addition of these higher level libraries, such as layers and estimators, we are moving to a world where there's a lot less complexity in the defining of models and even very complicated models like LSTMs. Okay, so TensorFlow is pretty flexible. You'll notice that the words TensorFlow do not include the words deep or learning anywhere in there. Certainly TensorFlow was designed as a platform that would support deep learning quite nicely. And so, auto differentiation is one of the key components of TensorFlow. But it supports a wide range of algorithms. As one project that I've been working on for a while, we support random forests that are actually similar to the wonderful MOA package that Alfred has put together. It's something that can be used to deal with a wide range of distribution schemes and used for a wide range of data types and data formats. Okay, TensorFlow is reasonably well integrated with a wide range of open source platforms. Because I'm not Martin, I'm actually not an expert on things in the open source world that are outside the Google walls. So I can't talk more intelligently here, and maybe some of you guys will have questions that I can't answer.